This lesson is about finding values for sigma squared and sigma, depending on whether your parameter is the standard deviation or the variance. Let me make sure that my captions are showing. They weren't, but my recording was on, so that's a plus. Okay, so the first thing that we want to do, I'm going to kind of review this a little bit. And there's some stuff in your notes that I need to show you, but we're going to be using the chi-square distribution for this. And if you remember, the chi-square distribution is right skewed. So it has a big hump on the left and it goes all the way down, which that's a very bad drawing of it. But this chi-squared values are always positive, and this curve is not symmetric. So this time, if you have a two-tailed test, you have to do two versions of it. We're going to be using that chi-square program that you used back in chapter 7 for the confidence intervals. That's going to come back also. Let me pull up what I want to show you, because she has a handout for this, not a, but a Canvas piece that I want to show you before we get too far into it. And if you don't have it, then I would suggest that you hold on, my view is that you pick it up, because it's going to describe for you how to, let me see where it is. Chi-square test for variance should be in my downloads today. Downloads folder. Okay, this is the homework. Where's the print that I did? I think it might be that. Oh no, that wasn't that one. It wasn't that. It wasn't that one. Okay, let me show. I can't find it, so let me find it on the let me show it to you on Canvas itself, because it's important for you to see that. Before we start this. So, okay, right here. So what you're going to need is for me to share the screen. But besides that, what we're going to need are these instructions here. Okay, the critical value and the p-value for chi-square testing. So remember, the critical value is going to apply when we're doing the traditional approach, and the p-value is going to apply when we're finding p-values. Okay. So we have instructions for a right tail test, a left tail test, and a two-tailed test. Pretty straightforward, pretty similar to what we did in chapter 7, but they're here. Okay, remember we have 2 of those. P-values, there's a little bit of a difference with that. When you're calculating a p-value that has 2 tails, okay, you actually pay attention to whether your test statistic is larger or smaller than the degree of freedom to decide which side of the distribution you're on. So we'll get to that when we get there, but this is where you find the instructions. They're also in the slides for this lesson. Okay, but I'm not going to go over the example problems. We have enough without using embedded tutoring time to do that. So the next thing that I'm going to share is, where is it? Here it is this thing here. Oh wait, that's not, yeah, but it's not the one that I wanted. Let me come back to download. So the first thing we're going to do is we're going to practice using those instructions that you just saw. That's the very first thing that she has us practice. So let's look at this first example. Don't be intimidated by the length of it. It's not that difficult. For those of you who are wondering, there is a separate video on the homework help, and we did do this problem. So if you want to watch it there, you can also watch it there. But repetition is the mother of skill. So we're doing this here as well. Okay, so let me get into my screen here, and I think we're there. So the first thing we want to do for question 1 is find the critical value or values for each. Show the critical and non-critical regions and state the appropriate null and alternative hypothesis. Use sigma squared or variance is equal to 225. So essentially what we're doing here is the first 2 steps of a hypothesis test. Okay, we're not doing the whole thing. She just wants you to get used to setting it up. And so you're going to do each part individually. All right. So part A, it says that alpha is 0.05, n is equal to 18, and we have a right tail test. Okay. So what that means is we have this. We have a distribution. Remember, chi-squared starts at 0 because we don't have negatives. And we we know that we have a right tail test. So we know that our chi, our critical value, I should say, not our chi, but our critical value is somewhere over here, but we don't know where it is. We don't know where this is. So our critical value is a question mark. But we do know what our alpha and what our degrees of freedom are. So if we go back, alpha is 0.05 and n is 18. So here, this is 0.05. This area is 0.05. And n is 18. So I'm just gonna put that up there. Now, we want to find what this critical value is. So based on our instructions, we know that we have a right tail test because she told us. And if you look at the instructions here, it says for a right tail test, chi-squared will be greater than 0, and your critical value is going to be inverse chi-squared of alpha and df. So For part A, we have one A. We have critical value is equal to inverse chi-squared alpha, which was 0.05, and DF, which is, remember, your DF is 1 less than N. So DF here is equal to N minus 1,
17.
which is 17. Very good. So now just plug it in. And we're rounding to 4 decimal places here. So 17. And
I got 27.5871.
that's correct. 27.5871. Very good. Now, the next thing she wants you to practice doing is, here's the drawing. The drawing is really more of an aid for you right now, so you remember kind of where this is. So we have our critical value. So she asks you in the instructions for question 1 to draw these. So go ahead and draw your distribution and put in your critical value, 27.5871, somewhere in the right tail, as you see on the screen here. And then just set up your null and your alternative. She just wants you to see that you're doing the setup there. I'm going to go ahead. You can start if you're ready, Jason. You can start on B. I'm going to mute myself for a minute. I'll be right back. Okay, so don't forget to write your null and your alternative. Your null here should be, she wrote the statistical equivalent, but your null is actually, you can use equal to, but it's actually less than equal to. We know that because it has to go both ways in your hypothesis test. Okay. How about B? B is alpha is 0.10, N is 23, and we're doing left tail test. Let me put up the instruction. So B is alpha is 0.10. For B, we have, I'll draw it below it. In this case, it's a left tail test. So it's over here. And this is this area here, we know, is 0.10. So alpha is 0.10. And we know that n is 23. So remember, we need df. N is 23, and we're doing a left tail. So now n is 23. That means our df here is 22. Okay. How about B, Jason? What did you get for B?
I did the inverse chi part.
Oh,
That's
okay.
pretty much it.
Okay. So what did you get when you did the inverse chi for the left tail?
The answer that you got 14.415.
041. Good job. Okay. Go ahead and draw your graph. And you're going to notice that your critical region is on the left. Your critical regions show up in the direction of your tests. That's been something that's been tripping some of you up recently. Okay. Moving on to letter C. Letter C.
Wait, I'm still
is-
writing
Oh, I'm sorry.
the
Take your time.
H0, and I don't get it. Is the sigma square always going to equal the number?
Well, she just gave you that as an example, so you would have an example to use. But no, this sigma squared will vary.
Oh,
When you, if you go to, let me show you something. We'll come back to this in a minute. That was a good question, and I can see why you thought that. Let me go to, uh-oh. Bear with me for a moment. I got my screen share got a little bit, one little out of hand here. Let me go and use this. Okay, I think if I shift here. Really, I don't want to do, okay. I don't want to do that right now. I'm going to go to files, which is this one. If we look at, let's try this. Here it is. If I look at question 3, okay, what is, it says test the claim that the standard deviation of the number of aircraft stolen each year in the United States is less than 15. My parameter there is the standard deviation. What is the value of it? What is my sigma in number 3?
0.05.
That's my alpha. That's my alpha. Sigma is what the standard deviation is.
Oh, 13.6. I wasn't looking.
Okay, okay. be a little bit careful there. This is something we're going to get into. This is the sample standard deviation. This is S. Okay. But it says test the claim that the standard deviation of the number of aircraft stolen each year is less than 15. Okay. So what we're going to see, and we're going to see this later, but my point is that this varies. This means that sigma here is 15 because this is the standard deviation of the population. This is sigma equals 15, and this random sample S here is 13.6. It turns out that when we do this formula, which we're going to do in just a little bit after we get done with the first two, that my sample standard deviation and my population standard deviation are both part of the formula. So you have to be able to distinguish this. If it's a sample standard deviation, it's S. If it's a population standard deviation, it's sigma, and it goes in your null hypothesis. But to answer your question, the sigma will be given to you in the claim, whatever the claim is. So like here, sigma is 15. In number 4, the standard deviation here is 1.2. Okay, so you can see that the standard deviation varies, which is what your original question was. Okay, so it varies. The reason that it's always 225, the variance for the one that she showed you here, is because she wanted you to be able to set up the hypothesis test. You wouldn't have been able to set it up if you didn't have a value for the parameter. Okay. So that's why that worked the way it did. Now let's go back and let's do, did you try part C yet?
No.
Not yet. Okay, let's see. Let's go back to part C of number 1 here. Okay. Alpha here is 0.05.
Oh, I wasn't done
You
writing
weren't done
down
with this?
B.
Okay, no problem. We can get that back for you. I just wanted to answer that so you would have your, let me come back to this one here. Okay. Now you part B, you said. All right, part B. Put it back up on the screen for you. And we can continue on as soon as I get myself situated. There we go. All right. So here is part B, right there. Okay. You got your critical value, that's 14. So then your critical region is going to be everything to the left of 14.0415.
Okay, that was it.
Mhm.
I just had to put in the left tail test.
No problem. So now we're going to go on to problem 3, or I mean, sorry, part C, problem 1, which here they give us our first two-tailed test. Okay, now she gives you the inverse chi instructions. I'm going to explain this a little more. C is alpha is 0.05, N is 15, and it has two tails. So here, if you remember doing chi-squareds before, we always used the inverse chi when we did values, and this is no different. But here, your chi-squared distribution, if you remember, starts from 0, which is why I drew it like that. And then it, as I mentioned, has that curve and comes down like so, right? Now, if it's got two tails, it means we're going to have two critical values. One here, we don't know where in the tail, but somewhere there, and somewhere over here. Okay. Now, this is one of those things, remember in your program that you use, it's the area to the right. Okay, this is the only, well, this is the only distribution you've seen so far that does this. So to get this left critical value, you're going to use, for this one, it's going to be equal to 1 minus alpha over 2 and df.
Hmm.
And obviously your inverse chi function, right? So it's inverse chi of 1 minus alpha over 2 and df. For this critical value, here we're going to use inverse chi of alpha over 2 and df. Okay. So you have to be a little bit careful there. You're going to have access to these instructions for the final. So don't forget, download them or use the slides to help you. You're not expected to memorize that. Okay. So going back to this problem, n is 15. That means that df is 14. She tends to get the right side first. That's just something that she developed from the confidence interval because it gives us a smaller value. It gives us a larger chi-square, but it gives us a smaller end of the confidence interval. So don't be thrown off by that. If you want to get the left side first, that's fine. But they're there for you to check on screen for those of you who are following along with the video. Okay. I'm gonna mute my mic one more time. I'll be right back, Jason. Okay.
Mm-hmm.
I'm back, Jason. So here,
Alright,
how did you do on the critical values?
I got them both correct.
Good job. Now remember, this is a two-tailed test, okay?
Mm-hmm.
So this one's gonna be equal versus not equal. So this she has correct, okay? This one is correct, equal versus not equal. But remember that if it's right or left tailed, you have, like for B here, if this is less than at the bottom, then you should have greater than equal to in your, I don't know if it didn't show up or she didn't type it, but it should be greater than or equal to
Which one
for
is
her.
this?
That's B. B, the
Oh,
null hypothesis for B. Just remember that you have, it has to go the opposite way, remember?
it's greater than?
For B, yes, because B is a left tail, right? So HO is B is sigma squared is greater than or equal to versus sigma is less than. Okay.
Okay.
C is correct.
Okay.
You see what happened?
Yes.
C is correct. She has C correct there. So then let me do this. Let me go down to, let me come down here and use the mouse. So C, we have equal to versus not equal to, and it's a two-tailed test. All right. Remember to draw your graph. We're only drawing graphs for this first one, and then when we do the traditional approach for that, okay? And D is another practice with a two-tailed test, because that's the one that's a little bit tricky for most people. So I'm going to leave this on the screen for those of you who are following along and learning to do this. This is part of the skill of doing hypothesis testing. She just isolated it so you could practice with the calculator, because this tends to be something that people get wrong and they don't know why. If you're not getting these answers, okay, check to make sure that you're using DF instead of N. That's very tempting to do. If you're in a hurry, sometimes you forget to subtract 1 here and you end up using, for example, 8 instead of 7. Okay, so watch out for that. We're doing here.
What?
How are you doing? Did you get these two?
Yes.
You got that? Okay. And how about the graph?
Doing that right now.
Okay.
There.
All right, so now that's problem one. Now what we're gonna do in problem two is we're not gonna draw the regions, but we're gonna learn how to find p-values. And then we'll have all the new skills that we need to do the hypothesis testing. And other than the formula, which I'll show you when we get there. Let me stop sharing this and share problem two from the screen here. So this is our second problem here. So this, share the screen, why don't I? Okay. All right, so here is problem two. We're finding the p-values for each indicated chi-square test statistic. So this test statistic, you don't have to worry about how we calculated it right now, because we're just assuming we got it from the hypothesis test and we're finding the p-value for it, okay? Now, the instructions down here are the same instructions you saw on the handout that I was showing you earlier. So for part A, chi-squared is equal to 29.321 and equals 16 and its right tail. Now, excuse me, when she made these solutions, she was using 3 decimal places for chi-squared. So go ahead and go with these, but just know that your chi-squareds will be 4. She asked for 4, but here, maybe this was given in the textbook and they gave it to 3. Sometimes tables give it to different numbers, and that could be why there's a discrepancy here, but that's the reason, okay? Now, if it's a right tail, then remember we're looking, in this case, we're looking at something that does this. Here we are on the distribution. Like I said, you don't have to draw it, but this will help you see what's going on. So this, oops, did not need that extra line there. Was doing fine without it. Okay, so here's my distribution. And it's a right tail. So wherever my chi-square, maybe it's there, okay? This is 29.321. So I'm looking at this. And I'm looking, remember, my p-values are associated with my area in my tail. So I'm really looking at this here. I'm looking at this area, okay? Now, if I want area under a curve for chi-squared, then I'm going to use chi-squared CDF. And for a right tail, I'm looking at the second bullet. So it's the p-value is going to be from my chi-square value, which makes sense, to infinity with my degree of freedom. Okay, so there's my chi-square number, 29.321. N is 16. Remember, we don't plug in 16. We plug in one less. because we're plugging in DF. Okay. So you plug in 15 and you get the p-value. No need to draw, no need to state your hypotheses here. But as I said, the drawing sometimes is helpful in helping you see what area you're looking for. Remember that the chi-square distribution is on your distribution menu. I believe it's number 8 on there.
What?
The chi-square is number 8 on the distribution menu. So if you
Don't you-
have,
Oh, don't you mean the x square CDF?
yeah, chi-squared CDF. That's correct. So it's second distribution, chi-squared CDF. For me, that's number 8. Be careful, chi-square PDF is right above it. You want the one with the CDF.
I already did it, and I already got 0.0146.
Good job. Nice job. So then let's continue. So here, let's go on to B. B is chi-squared is 10.215 and is 25, and we're in the left tail. Okay, so here we have, here's my chi-square distribution. This time
Do I have to draw the graph?
no, you don't.
Okay.
I'm just showing you where the region would be. This region is this way. Remember, we don't have negative infinity for this because we don't have negative number. So we start at 0, okay? So this starts at 0 and goes to the chi-squared number that she gave you. So it's chi-squared CDF from 0 to 10.215 with your DF. Clear?
Hold on 1 second. 0. Yep, I got the same thing.
Cool. All right. Now we have a two-tail. Okay, we've done some of that before. So we're going to have 2 separate chi-square values, and we're not going to be able to get them at the same time. So we're not going to be able to just flip them like we normally do, because they're both going to be positive and they're going to be different. So we have to do a test here to see, because notice this is the one that I told you we were going to discuss a little bit when we got here. It depends on, we double it to get the p-value. We know that we've done it before, but which one do we double and how do we know where it is? Well, you look at the chi-square value and you compare it to your degree of freedom. So if you look at C, it says that chi-squared is 24.672. Okay. N is 11, which means that DF is 10. So here, my chi-squared is much bigger than my DF. And when that happens, when your chi-squared is bigger than your DF, you end up doubling the right tail. So in this case, you would have something, because we don't know where that chi ends up, but it ends up being in the right tail because of her instructions right here. If chi-squared is larger than the derivative, then your p-value is twice chi-squared CDF from the chi-square value to infinity. So chi-squared would end up over here.
Mm-hmm.
Okay. All right, and then we have a left critical value. And that's going to be from 0. You're going to,
So I come
but
up with
your p-value is what we end up doubling. So your p-value, you only get 1, but you have to double that number. And that's why we multiplied it by 2. So this one, let me scroll down so we can see what's going on here. So then let me roll up. Okay. And I think we have one more. Yeah, we have one more p-value. It's a right tail. So we don't double anything here. We're just going from the chi-squared to infinity. So
I'm still writing number C.
that's fine. Take your time. I think a lot of this will make a lot more sense when we do a hypothesis test, then you'll see how it fits together. That'll make better sense to you. Why we had to know this first.
There.
Okay. All right. Now we get to,
Oh wait, I wasn't done with D.
oops, my apologies.
That's fine.
No worries. There's D here.
All right, finished.
Okay. All right. So now we're actually going to apply all those skills that we just used to an actual hypothesis test. So let me make sure, hold on. Let me get the homework assignment. And I'll bring up the Number 9 is going to be in a separate video, so I won't do that one. It's raw data. We'll do a different one. But let me see where the homework is, because there it is. Okay, so the next one on our list here, we referenced this earlier. Okay, so maybe we should do this one. We kind of had a little preview of it earlier. But let's see what we can do with this. So I'm gonna say, here's my problem. Let's take a couple of notes on it before we go to the whiteboard. So it says, test the claim, okay? Can't be more explicit than that. Test the claim that the standard deviation of the number of aircraft stolen each year in the United States is less than 15. So my claim is sigma is less than 15. If a random sample of 12 years, S is 12, N, random sample is 12, had a standard deviation of 13.6, and use alpha equals 0.05. So let me show you how this works. Test the claim that the standard deviation of the number of aircraft stolen each year is less than 15 if a sample of 12 years had a standard deviation of 13.6. So we do what we always do when we do a hypothesis test. So we're going to start with, what is the parameter? Well, the parameter in this case is what? Population what?
I don't know.
Okay, when you're answering, what is the parameter? Let me come over here to another, because this is a question that you're not the only one to have this question, okay? When you're answering, what is the parameter? And you're gonna see this on your quiz, you're gonna see this on the final. The answer to this question, think of it as a multiple choice question without A, B, C, D. It's gonna be a mean. It's gonna be a proportion. It's gonna be a variance. Or it's gonna be a standard deviation, but it's not gonna be the word, it's gonna be the symbol, okay? So the symbol for the mean, we know, is mu, right? The symbol for the proportion is P. The symbol for the variance we were doing earlier is sigma square. And the symbol for the standard deviation is just the sigma without the square. It's going to be one of those four.
Standard
So
deviation.
it's going to be the standard deviation sigma, correct? So this is going to be the population standard deviation. And you do need, for those of you who are wondering at home, you do need to write this out. This is part of the instructions. So population standard deviation. And you're going to write the symbol, which is sigma. Okay. Now, the next thing is we need to identify the claim. If you remember what we just read, it said test a claim that the standard deviation was less than 15. Now, if it's less than, we know that it goes with H1. So H1, we're going to say sigma is less than 15. Then we're going to write down what approach we have. Since they didn't specifically tell us to use an approach, we're going to do the traditional approach or the traditional method. Okay. If you write traditional approach, traditional method, they're the same thing. Now, I didn't show you yet what the formula is for the test statistic, but when you do your givens here, we need sigma, obviously, but we have that already. So we need sigma. Sigma is 15. We also need two other things. We need our S. And remember, this is a standard deviation as well, but it's the standard deviation of the sample that you took. Okay. She tells you that the population standard deviation is 15. The sample standard deviation was what, Jason? Do you remember?
13.6.
13.6. That's S. Okay. And N is 12. Okay. So we have this is 13.6 and N is 12. And our alpha, was it 0.05? I believe so.
Alpha is 0.5.
0.05. Okay. N is 12, which means DF will probably come in handy. In fact, it will. So go ahead and make a note of it right here. DF is N-1, which is 12. Sorry, 11. And then
Yeah.
your alpha is 0.05, and we're ready to go. So we don't have nearly as many givens. We don't have as many unknowns in these type of problems usually that trip us up. So we're there. Okay. Now let's write our first step is always write the null and the alternative hypotheses. So step one. There's my, put your step number in a box. So here you have HO. If your H1 is going to the left, your HO is going to go to the right or greater. So this will be greater than or equal to 15. Okay. And your H1 so H1, and I've forgotten my sigma. How inconvenient. Let me put it in there. Sigma. Don't forget that like I did. Sigma is less than 15, and we know that's my claim. That's what we're looking to prove. So this is my claim, and it's a left tail test. Okay. Now, and you want to make sure that you also write your statistical equivalent. I have a feeling that's where she got all her equal signs from, because she started writing her statistical equivalent to that. So your statistical equivalent is HO sigma equals 15. Now we're going to do our critical values, and we practice that in problem number 1. So we're going to practice that here. We're going to say that we have a left tail test and our alpha is 0.05. So sigma equals 15 here. Oops. Thought I had not drawn that, and it took extra time to appear than I was expecting. So this is 15 here. All right, so step 2 is we find the critical value. Whoops. So which side is my critical value going to be on?
Critical value. Less than.
Yeah, it's going to go to the left because it's less than. So I need to follow the procedures for finding a critical value for a left tail test. So my critical value here going to be critical value. It's going to be inverse chi, remember. And since it's on the left, it's going to be 1 minus alpha and your df. So here, my critical value is equal to inverse chi 1 minus 0.05. And what is my degree of freedom here?
11.
Right. Go ahead and put that in your calculator. And I'm going to
I got 4.5748.
do a quick swap and I'll tell you if you're correct or not. But I believe in you. Let me just make a quick swap for the number here. And I think we'll be good. Oh, that's not the one. Okay, here's my, let me share this on the screen and we'll see how we're doing. So okay, there's what we have so far. Notice I have my statistical equivalent. I have left tail test, I have claim. I have 1 minus alpha DF, and you're correct, Jason, 4.5748. Good job. Now, the other new piece to this is your formula, okay? Not a very hard formula at all. It's n minus 1 times s squared over sigma squared, okay? S is your sample standard deviation. Sigma is your population standard deviation. And you're actually using the variances in the formula because we're squaring it, okay? If you remember, she gave you S from the problem. We have S. S is 13.6, and sigma you have from the claim, from the null hypothesis. Sigma is 15. So when you put this in your calculator, no real need for parentheses. You can subtract 1 from n without needing a calculator. So you can put that number in directly like she has here.
I already did. I got the same answer.
Now, when we do step 4, then we're doing the traditional method, we do draw. Okay, so we reject HO or do not. Remember this step, you're going to have, what you're going to have on your screen is you're going to have this, you're going to have reject HO or do not reject HO. All right. If you want to circle one, if you want to write it, that's fine. It just means there's going to be a little more writing if you write it. Now, what happens here? Remember, your critical value was 4.5748. Your test, though, is going to the left, not to the right. Your test is going to the left. So your critical region is this region in the corner. Okay, it's not this big white region. Chi-squared is 9.0425. Chi-squared is bigger, so it's outside the critical region. It's, remember, this is the non-rejection region. So we do not reject HO because the test value falls in the non-critical region. Okay. You do not reject it because it falls in the non-critical region. Okay. And therefore, we can now write our conclusion, knowing that our claim was H1, okay, we can say that our claim was H1 and we failed to reject HO. Here's your little flow chart. We haven't had the flow chart make an appearance in the video. This is the flow chart for the decision chart for writing your conclusion. Use exactly what's in the box, whichever statement applies. Here, since the claim is H1 and we did not reject HO, we say there is not, and we underline is not, enough evidence to support, because our claim is H1, support the claim. Okay, and that's it for that. I think we have time to do one more. So we'll do number 4, okay? Okay, let's do this. Let's take number 4 so I can show you that. We're gonna go to this one here. And I think we saw this one earlier as well, when you were asking about is sigma always the same number? This should help you break that myth for those of you who had the same question. Whoops, let me go full here. All right, here it is. It says, manager of a large company claims, there it is, that what? The standard deviation of the time in minutes that it takes a telephone call to be transferred to the correct office in her company is 1.2 minutes or less, So it includes the 1.2, but it's or less. A random sample of 15, that's my N. Calls is selected, and the calls are timed. The standard deviation of the sample is 1.8. Okay, at alpha equals 0.01, what? What are we testing? Here it is. Test the claim that the standard deviation is less than or equal to 1.2 minutes. Use the p-value method. Okay. So this will be good. This gives us a chance to look at the p-value method. So again, start like we start every hypothesis test. What is the parameter of interest? It's the standard deviation sigma. Remember, your parameter is going to be one of those 4 that I showed you on the previous whiteboard. Okay. Since your claim is that the standard deviation is less than or equal to, the fact that you have the equal to makes this part of the null hypothesis. Okay, so sigma is less than or equal to 1.2 is my claim. And all she did here was record the givens. And we want to put in, we also want to put in the approach that we're doing here. So the approach is going to be traditional method or traditional approach, something that lets her know that you thought about. I'm sorry, that's wrong. It says do p-value. My apologies. It says do the p-value. So you're going to write the approach is the p-value method. Approach is going to be p-value method. All right, so then you write the givens. We know how to do that. Not hard, okay? She gave them to you from the problem. Now, the next part of this, you're going to write your null and your alternative. Your null is already there. There's your claim. Your null is already there. Just add HO to it. So I'm going to scroll down. Okay, let me get rid of the. All right. So my first step, my sigma is less than or equal to 1.2. Don't forget your statistical equivalent. You're going to say that HO, your statistical equivalent here is HO is sigma is equal to 1.2. And it's a right tail test. Okay. Now your test value Now this time we're practicing a skill that we used in number 2. So the chi-squared test value. Remember when we're using the p-value approach, before we get the p-value, we have to get the test statistic. So we have to use our formula here, okay? There's my formula. Let me get rid of my formula is the same one you're used to. I just have to plug the numbers into it, okay? N is 14. Was N 14 or was N 15? Did she? Oh, no, N was 15. So N minus 1 is 14. So 14. My sample standard deviation was 1.8. So we square it. And my variance is 1.2 squared there. Okay. Take a moment, do this in your calculator, make sure you're getting 31.5 for that.
Yep.
Now, the p-value this is practice from what we did earlier. This is a right tail test. So you're going to go to your distribution menu, find your chi-squared CDF, and you're going to put into the chi-squared CDF, you're going to put your chi-squared that you just calculated. Then you're going to go E99 and you're going to have degree of freedom is 14. Okay, you don't have to double this because it's not a two-tail. So you don't double it, you just plug it in and let the number crunch work for you. Okay.
0.0047.
Perfect. Good. Now, do you remember how we make decisions in the p-value approach?
If the p-value is greater, you reject it. Or
Other
less
way,
than.
if the p-value is smaller, you reject it. If the p is low, the hoe must go. That's how it works. Okay. So if it's smaller, you reject it. If it's larger, you fail to reject it. You do not reject it. So in this case, your p-value is much smaller than your alpha. Right? P is much smaller than alpha. So you reject HO because the p-value is less than alpha. Okay. So don't forget that. And we don't need to draw, but you do need to show this comparison. Okay. And then because you rejected the no, remember your claim was H1. Your claim was HO this time. So again, here's your flow chart. Your claim was HO, you rejected HO. So in this case, there is enough evidence to reject the claim. There is enough evidence to reject the claim. Okay. And that's really all there is to that. It's not too hard. Okay. I'm gonna